work of me, Alexander Baxt, and Ranjit Sala. So I'm going to start with a small verification example. Here, I define a function increase twice that just increases its argument by 2. And I'm using this function to create two assertions. So my first assertion says that if I increase 40 twice, then I get a value that's exactly equal to 42. And the second says that if I increase twice minus 50, then I get a negative number. So my goal is to automatically verify these two assertions. And to do that, I can use SMT solvers. So an SMT solver is just a black box that takes as input some formula drawn from a decidable logic, and it replies valid if the formula is always true. Otherwise, it replies invalid. So for verification, first I need to give an appropriate specification to my increase twice function. And here I use refinement types to give it a specification that says that increase twice takes as input a variable x, that is an integer, and returns a value r that is exactly equal to x plus 2. Now, with this specification, I can go on and verify my client, because I know that p is a value that is exactly equal to 40 plus 2. So I want to prove that p is exactly equal to 42. So I can just ask the SMT solver if this implication is valid, and the SMT solver will happily say that, yes, my implication is valid. So we can use SMT solvers to have automatic verification. And this is the reason why I love SMT solvers. And of course, it's not only me. So SMT solvers have been successfully and extensively used by many tools to provide for automatic verification. But still, I have a problem with SMT solvers. And my problem is that SMT solvers generally require decidable logics. And this means quantifier-free first-order logic that generally constrains the specifications to be non-modular. So as an example here, I tweak my client, and instead of using increase twice, I create my increase twice function by composing two functions, both of which increase their argument by 1. And now to verify my assertion, I need to give an appropriate specification to my compose function. So as a first attempt, I can give compose a first order specification that says exactly my requirements, that if I give compose two functions that increase their argument by 1, then I get back a function that increases the argument by 2. But of course, this specification constrains compose to only accept functions that increase their argument by 1. So I don't like the specification because it's not modular. So as another attempt, I can give compose a higher order specification. For example, I can say that for every function f and g, compose just returns the composition of these two functions. So the problem now is that I use arbitrary functions in my specification, and this means that I can get outside of my decidable logic, so then my specification is not decidable. So my problem is that I have to choose between automatic verification that uses first-order logic and is decidable by SMT solvers, or modular specification that generally uses higher-order logic. So my goal is to have automatic verification of modular specifications. So towards this goal, we make a key observation, that is that refinement types are relations. So for example, this refinement type says that my output y is equal to my input x plus 2. So this is actually a relation between my input x and my output y. So my first step is to abstract over these relations. So I can have a refinement type that says that my output y satisfies an abstract relation p over my input x. And then for the SMT solvers, this p is just an uninterpreted function. That is just a function that satisfies the congruence axiom that says that if I give p same inputs, then I get same outputs. And then my second step is to constrain these relations so that I can specify concrete properties for my abstract relation p. So this is our key idea that is very general, but we can go back to the compose example to see how these steps apply. So here I have my first order specification of compose that is very concrete. And I have a concrete first order relation. So I'm going to abstract over this relation and say, for example, that the first argument f is a function that satisfies the abstract relation P for every relation P. So now this is a very abstract type for compose. And the question is if this specification is correct. So our next step is to go and check if this specification is correct. So how do I check it? I say that I know that my first argument is a function f that satisfies the predicate P. My second argument is a function g whose output satisfy the relation P on x. Then I know that I have as input some value x of type A. And I also know that my intermediate value y satisfies the predicate P on x because I got it as a result of applying the function g. Then I know that my intermediate value z satisfies the predicate P on y because I got it as an output of the function f. And with these assumptions, I need to prove that my result z satisfies my relation P on x. So I have these statements, and I'm going to turn them into an implication and ask the SMT solver if this implication is valid for every relation P, Q, and R. Of course, the SMT solver is going to reply no, because the specification I gave to compose holds for every relation P, Q, and R, so it is very general. So our first step was to abstract over relations, and this took us to a very general specification that is missing this concrete implication so that verification of compose is good. So our next step is to use this implication to actually constrain our abstract relation. So to do that, I'm just going to define a bound chain that chains my abstract relations P, Q, and R using this concrete implication that I'm missing. So now I can use this type to fix the type of compose. So previously, the type of compose holds for every abstract relations P, Q, and R. But now I'm going to modify it so that it holds only for relations P, Q, and R and actually satisfy the bound chain. So now if I have this modified type, I have in my precondition that P, Q, and R satisfy my bound chain. So I can put this into my assumptions. And now I have extra information. So if I turn these assumptions into an implication, I can go again and ask the SMT solver, is this implication valid? And the solver will reply yes. So this type of compose is OK. And we saw how we can use this type of compose to have decidable verification. Then my next question is if this type of compose is modular. And to answer this question, I'm going to pick up a random client and try to verify it. So I'm going back to my increase twice function. And I get increase twice by composing two functions that increase their argument by 1. And I have my desired specification for increase twice. So I need to verify this client specification. So to do so, I use some inference so that I appropriately instantiate my abstract relations P, Q, and R. And then I need to check that these concrete instantiations actually satisfy my bound chain. To do that, I just go and replace my concrete instantiation to the bound chain. And again, I ask the SMT solver, is this implication valid? The SMT solver will say, yeah, the implication is valid. So the signature of increase twice is OK. So we saw an example of our key idea. That is that we observe that refinement types are actually relations. And using this observation, we go to at the library side, we go and abstract over these relations. And then we constrain them appropriately. And then at the client side, we need to first instantiate our abstract relations, and then use the instantiation to check if the constraints are satisfied. So my goal was to have automatic verification of modular specification. And to achieve this goal, I used constrained or bounded abstract refinements. And then we'll go and see some applications. So we already saw higher order functions. So we saw compose. And then we can use bounded refinement types to specify and verify foldr and filter. So I'm just going to present the specification of foldr. So foldr is a function that starts from a basic value b and uses f to fold my list. So when we want to specify foldr, we observe that we need two abstract relations. First of all, we need to specify that a value b satisfies an invariant on the list axis. And then we need another relation that says that if I use the function f on my list element x and my current accumulator b, then I step to b prime. So I'm going to define an inductive bound on these two relations that actually encodes induction on lists and say that if I know that the value b satisfies the invariant on my tail, on my list axis, and I also know that from b I step to b prime using the head x of the list, then I know that b prime satisfies the invariant on my list x cons axis. So this bound directly encodes induction on lists, and I can use this bound to give a refinement type specification to my foldr function. So my specification says that for every abstract relation invariant and step that satisfy the bound inductive, if foldr takes as input a function that follows my step relation, and also my basic value satisfies the invariant on the empty list, then the result of foldr satisfies the invariant on the input list axis. So we saw some applications of bounded refinement types to higher order functions. And then we used bounded refinement types to both specify and verify database schema and queries. So our goal was to provide modular specifications for database operators like select, project, and join. And for that goal, we used abstract refinements to describe generic key-value relations. And then we used bounds to describe schema properties on these relations, like disjointness and union. So as another application, we use bounded refinement types to specify and verify floor-hole logic in the state monad. So again, our goal was to provide modular specification on state operators, like sequence, if, while, and for. And to do so, we used abstract refinements to describe generic state assertions. And then we use bounds to specify that these assertions satisfy the floor-hole constraint. So in this application, we refined the state monad so that it satisfies floor-hole logic. And on top of that, we built a client. We built as a client a refined I/O monad that tracks capabilities. So we saw some applications, and then I'm going to make some notes on the implementation. So we built bounded refinement types on top of Liquid Haskell, a liquid type checker for Haskell code. So I'm not going to say anything more on Liquid Haskell, but there is a CAP tutorial on Thursday if you want to learn more. So given Haskell, building bounded refinement types was quite easy because we observed that abstract refinements desugar to ghost variables and bounds desugar to ghost functions in a way very similar that Haskell uses to build the type class dictionaries. So my goal was to have automatic verification of modular specifications. And to achieve this goal, I used constrained or bounded abstract refinements. So bounded refinement types turn out to have a lot of applications, including higher order specification and verification of higher order functions, database, and floor-hole logic into the state monad. And implementation is quite easy because bounds just desugar to ghost variables in a way similar to Haskell dictionaries. So in the paper, you can find more details or common questions like how do we prove soundness, how fast is bounded type checking, or how easy is it to come up with the bounds, what are the limitations, and why do we care so much about decidability. And with this, I want to thank you and take questions. Okay, so we had liquid Haskell that was quite expressive already. So we added bounded refinement types, and we were able to specify and verify things that we were not before, like compose of fall. But we still have many limitations in liquid Haskell that are not directly related to bounded. But for example, we cannot describe types inside the specification, or we have functions only in the way of uninterpreted functions, and this limits how much we can discuss about functions. So these limitations still exist. But
So in step 4 of your 4-step process, the client bit, you have to instantiate compose, or the function you're calling, at some suitable instance of the abstract predicate. Now, I don't understand the details here, but type inference systems can often go to a lot of trouble to infer the instantiating types, and it's often not very easy to do. So, is it easy for you to infer the instantiating abstract, the predicates that instantiate these abstract things?
Yeah. So for us, it is easy because we use all these liquid type inference mechanisms that we were using already. So in short, how liquid types work is that you have a type, and in the refinement part, you have just a liquid variable. So we already have a fixed point iterative algorithm that goes and does all these instantiations. So we treat these abstract relations basically as these refinement variables, and we use all the existing mechanisms to get the instantiation.
Okay, cool. I'm glad it worked out.
So we've been using a similar style in F-star for several years, where things like your compose and your fold examples are written very similarly in F-star, except instead of insisting that they're relations, you can just quantify over an arbitrary predicate and write, it's a higher order logic, you can write constraints over those predicates and so on. Can you say a bit more about what the advance is in this work over what we've been doing in F-star?
So I guess my answer would be that we just take a different approach. Like from the beginning, we say that we want to stay in the decidable logic of the SMT solvers, and the reason for that is first of all because we do this we do inference, which asks a lot of queries to the solver. So it is our decision to have predictability, to say that whatever the queries we send to the solvers, we know that they will always come back. And the other thing is that our choice is not to depend on the concrete solver. So there are many heuristics, and I'm sure that Z3 is very good at even in theory undecidable fragments. But we want not to depend on the heuristic, but be able to give the same answer no matter what the solver is.
But surely to verify typical programs, you must eventually add quantifiers in some places. Say you want to prove quicksort on arrays.
So the short answer is we want to make every VC query follow the cycle. So I guess this is the question. Dive into question 4. The main advance we want to call it that is we want to do these fancy higher order things, but we insist that every VC query that is made belongs to the cycle.
So if you wanted to, you just forbid writing. You forbid talking about arrays, for example. You will forbid talking about arrays.
We let you talk about, actually this machinery also lets you talk about arrays in interesting ways. But this is one of the lines in the sand we draw, is that every VC query must follow the recycling fragment. So in a sense, we want to be able to do the kinds of nice things we can do in F-star while staying on the side of the line.
I see. So can I think of this as carving out some fragment that is always going to behave that way? Okay, thank you.